So without further ado, we will begin our first session. And to introduce our speaker, we have board member Yamil Rosete Rodriguez, who will introduce Dr. Ian MacDonald. Thank you.
Yeah, hi, good morning, everyone. Yes, my name is Yamil Rodriguez, and I serve on the board of the Choroideremia Research Foundation. And today, I have the pleasure and the huge honor of introducing Dr. Ian MacDonald. Dr. MacDonald is currently the director of the Department of Ophthalmology at the University of Montreal and holds the Suzanne Verona Trautmann Chair. He first trained in medical genetics, followed by ophthalmology in Canada. He has enjoyed working with patients and family affected by choroideremia since the early 1980s. He is also an Emeritus member of the Choroideremia Research Foundation Science Advisory Board. Please, welcome Dr. MacDonald.
Thank you very much for that very warm welcome. This is not my first time in Minneapolis. Minneapolis, a Twin City, home of, I believe, St. Paul was the home of Charles Schwartz, who I start the day off with reading the Peanuts cartoon. And it's a great privilege to be with you today and for the next few days. I missed the last event. I apologize for that. There's no apologies needed, I think, amongst family. Please call me Dr. Mac. I'm pretty sure I know who in the room gave me that introduction. So this is, we did, I think, Choroideremia 100, and so this is Choroideremia 101.2. And so my outline for the day, or the 20 minutes, is what is choroideremia, where have we been, where are we going, and okay, we're almost there. So part one, what is choroideremia? So choroideremia is, it's not an emia, but that was the name that people in the past thought it was due to. They thought it was due to something that was circulating in the blood, but it certainly isn't part of the choroid that's circulating in the blood. It's a rare disorder. It's an inherited retinal disorder. It affects all races. It affects women and men. It's sex-linked, so the boys and men tend to be affected more than women. And but how common is it? Well, the Arvo Mylearn says it's a cause of about 1% of all inherited retinal disorders. Either I'm in the wrong place, you're in the right place. I'm not quite sure why the feedback. Okay, thanks. Are we okay? Close to the microphone. Okay. A little louder. Oh. I'm sorry, I'm Canadian. Two words. You will understand it. And remember, we're your northern cousins, and I have American cousins, and it's just great to be here. So there are some lookalikes for choroideremia. That there's a disorder called Refsum syndrome, which includes hearing loss, and there's an autosomal dominant form of RPE65, the gene that causes Leber's congenital amaurosis, for which there is a gene therapy. But really, choroideremia is an ocular disorder. There are some rare cases of choroideremia with heritable hearing loss because it knocks out two genes, but this is a single gene disorder and it affects vision. So how do we see? You all know how we see. I know how I see. I see with two eyes, binocularly. I see an image in front of me. I have a visual field. I have a visual acuity. And so what is the layer of the eye that's most important for patients with choroideremia? It is the underlying layer of the retina, the retinal pigment epithelium. This is a cell layer that is super important. Underneath the retinal pigment epithelium, there's a vascular layer called the choroid. That's the word that we get choroideremia from, but it's not really the choroid that's completely involved in this disorder. It's that layer undergoes a degenerative process as the retinal pigment epithelium, the overlying layer of the choroid, is impaired. The retinal pigment epithelium is a single cell layer. It's very important. It's the layer that regenerates all the biochemical pathways of vision. The photoreceptors sit on top of that. The photoreceptors are the layer of the eye that accepts light, amplifies the signal, and sends it through a cascade to the visual pathway to the brain. The retinal pigment epithelial layer is important because it's regenerating the biochemistry of vision. It's also nibbling off the tail ends of the photoreceptors and regenerating all the components from the photoreceptors as well. So if we look in the back of the eye of a patient with choroideremia, we can see that the retinal pigment epithelium is significantly disordered both in the female carriers and in the male affected individuals. The central vision is maintained for a very long time, and that's because the central area of the retina, the macula, is preserved. The retinal pigment epithelium is healthy in that area, and that's the area that allows us to see well, to see faces, to read, but it doesn't really have a role to play in the peripheral vision. That's the peripheral part of the retina that's helping accomplish that. Choroideremia is a disorder that results from the absence of a protein called rhabis protein 1. It's a binding protein that's enabling messaging within the cell, especially within the retinal pigment epithelial cell. This protein, REP1, rhabis protein 1, makes it like a postage stamp for other proteins and allows trafficking, the recycling of components of vision within the cells. So what does it look like? In the preteen, you can see these areas of loss of the retinal pigment epithelium that tend to become progressive. For those of you who are sighted, you can see that there is a marbling or a mottling of the retinal pigment epithelium layer. And in an 18-year-old, this mottling becomes more significant and the retinal pigment epithelium becomes less involved. Becomes more involved. And you can see here that the central retinal pigment epithelium appears normal. Here's a 28-year-old, and you can still see the small area of retinal pigment epithelium right in the middle of the photograph. And beside that, there's an image of the visual field of the same individual. And you can see there's like a bullseye that's an area of lost visual field. The peripheral field is still okay. For the female carrier of choroideremia, there are areas in which the retinal pigment epithelium is not working as well as it should, but it's enough to maintain a good field and usually a good visual acuity. If we shine a light into the eye and have the retinal pigment epithelium absorb the light, it fluoresces back and we can capture that image. And so on the right, you'll see a sort of a black and white photograph, and you can see that the retinal pigment epithelium in certain areas isn't fluorescing, so it's dark. And so this is very typical of a female carrier of choroideremia. So how does the visual function change with age? Well, the changes occur in these two areas, visual field and visual acuity. And the visual field declines somewhat rapidly until about the age of 20, and then it declines more slowly after that, and on a linear basis. The visual acuity remains relatively stable until perhaps 50, and then it declines more rapidly. Of course, there's individual changes in individual patients, and it's just a general suggestion. So I thought we'd talk a little bit about gene therapy in our 101 talk. It's the introduction of a normal copy of the gene into the cell, and many of you are aware of the gene therapy experiments that have been conducted. It uses a vector, something that can carry a gene into the cell so that the cell will use the template to make the normal gene product, the rhabdiscoid protein 1. It is a disabled virus, so it's an immunogen, so it's the potential that it could cause harm from inflammation. And you can see here there's a scan of the back of the eye with a space in between the retina and the retinal pigment epithelium, and that is the space in which the vector is put into the eye. And so the cells are taken up by the retinal pigment epithelium. Those cells then use the template to make a normal gene product. So how would we treat a patient with choroideremia in a clinical trial of gene therapy or another trial? Well, we'd first have to test for a mutation in the gene. And these tests are available both commercially and available throughout North America. We'd have to test whether the vision is sufficient to undertake a trial, and we want to test the responsiveness of the retina. So here's a 40-year-old male with choroideremia. You can see there's a small area of retinal pigment epithelium that's remaining, and we were trying to understand whether we should treat that area. If we treat someone with choroideremia, we'd have to really go after what are the risks, what are the benefits, what do we know, so that the person would understand whether they wanted to be enrolled in a clinical trial. So these are not treatments, these are clinical trials, these are clinical experiments. And we did a clinical trial in Edmonton. Edmonton has a West Edmonton Mall. It's the sister mall of the Mall of America. So just another little fun fact. So I'm not in Edmonton anymore. I was there for 32 years, and here I am off in Montreal. So we started the trial in 2015 and wrote about it, and here it is 10 years later. And so I'm going to take you into part 2. So where have we been? And well, we've been in lots of areas. We were in the Outer Banks, and there's 3 blind men here. Actually, there's 2 blind men, and there's one taking a photograph. And 2 of them are in the room today. It was a wonderful experience. Raising money to create a clinical trial, and many of you participated in different ways, and thank you very much for all the support that you have given to me and others in bringing treatments towards choroideremia and a greater understanding of this. Our clinical trial in Edmonton was important. It taught us things. It taught us things for the future. We treated 6 individuals. 2 of them, unfortunately, had inflammation as a result of the vector and didn't benefit. And the others, perhaps one, has had stabilization in one eye. So we've been to many places, Albany in 2002, New Orleans, Chicago, Baltimore, France, the Outer Banks, Seattle, Boston, Denver, Philadelphia, Dallas, and Rochester, which I missed, unfortunately. But I wanted to read this to you. This is from Corey MacDonald, the son I never had. Wished I had as a brother, actually. And so here are his words. when we formed the CRF in 2000, there was no real research being conducted. Patients were diagnosed and followed, but with no real hope for a treatment or cure. We didn't even have an animal model to do research. We went from nothing to the first patient being treated in a clinical trial in a short 10.5 years. That's almost traveling at light speed in the world of disease research. Although we don't have an approved treatment yet, we know it's just a matter of time. There is real, in caps, real hope for our collective futures. I'm reminded of something Dr. Bennett said in Seattle. We've gone from a question of if to a question of when. Well, happy anniversary, happy 25th anniversary, because the CRF Foundation was started in 2000. And so balloons are up, and so quickly, where are we going? Well, here are some thoughts. Gene therapy with viral vectors by subretinal or intravitreal injection have been less than successful than predicted. There's still hope. Inflammation must be controlled. Agents that protect the retina, and in particular the retinal pigment epithelium, are important. And so I think the issues of precision medicine should be revisited. There's the possibility of gene editing, and there are RNA therapies that might treat some of these specific genetic variants in the choroideremia gene, and I'll talk about that. So finally, your investment in research is paying off in many, many ways. So please send me your comments to improve this presentation. There's my email address. You can find me probably on the web. If you can't find me, Corey will find me. And also be aware that I'm writing a book. And in the book, John Oster's words are included. I'm very unfortunate that John is not with us today. And I'd be pleased to include any words of yours. And so thank you very much, and I'd be open to questions, and I hope that there's a little bit of time for questions. Thank you. Thank you. Thank you very much, Corey. Happy to be your father. That's overwhelming. You probably have a sense of why I'm here, in the sense of choroideremia has been something I've worked on since the early 80s, and taking it from gene discovery to clinical trial was something that I had never conceived would be part of my journey, but it has been wonderful to meet many of you, to hear your hopes, to know your struggles, and to have been supported by you. Thank you very much. And so let's come back and talk. Let's talk together, though. I'm very, very privileged to have met and worked with many of you as families. Okay, that's enough. I'm not talking loudly enough either. So go ahead. Who's going to be up for the first question? You can. I don't know if there's a microphone.
Hang on 1 second. We're getting a microphone.
Yes, go ahead.
Oh, okay. I'm sorry. Thank you. I just wanted to know, as far as a carrier goes, is it a totally diagnostic looking into the eyes versus maybe having a DNA sample blood drawn? What are my
thoughts on that?
Yes.
I would say that early on, if there had been no family history of choroideremia, then the ophthalmologist or optometrist or optician might be a little confused and say there's a retinal dystrophy. But if there's a family history, then it's quite diagnostic. So if there had already been a family history of choroideremia, you could be typed as a choroideremia carrier at an early age in the teens. But molecular genetic testing is really the gold standard, and it should be available. Is that?
Yes, thank you.
Okay.
Thank you.
Morning, Dr. Matt. Okay, it is on. I could just yell. Could you address the topic of the variance in progression rates for CHM and the wide variance? That's a
Right.
topic that comes up a lot in the support network.
It does. And I think there's some nuances here. I don't want to I'll get into the details. How's that? So a gene is made up of DNA. DNA has coding sequences called exons. It has a promoter. It's something that drives the gene. There are intervening sequences in between the coding sequences, and there are sequences at the end of the gene. There's a whole array of different changes in the gene. They can be single point changes in the gene. There can be changes in the exon, changes in the intron, and I'm already off topic, and I do apologize. So all of these result in a relative absence of this protein product, Rabascore protein 1. You can delete the whole gene. All of these result in choroideremia. But why is it that in some families, I know of one family, and you know who I'm talking about, those of you, there are 3 boys, and they're not, you would think that the youngest would have the least choroideremia, the next oldest would have a little bit more signs of choroideremia, and the very oldest would have more severe disease. Well, that was not the case in this family. 3 boys, all carrying choroideremia, all with the same variant in the gene, but there's some differences. And I don't want to get too far off topic here. So we did a correlation across all the mutations that we knew to see if there was a correlation that, well, for this variant in the gene, that's going to be more severe. Another variant, oh, that's milder. There is no correlation in choroideremia. It probably has to do with the infinitesimally small amount of protein that is produced in some cases. And I can talk a little bit more about this later if you let me. But I want to tell you about another story because this is important because it led me maybe in the wrong direction, but maybe in the right direction. There were 2 men that I met in New York, both with choroideremia. One was on a statin, and it seemed that the brother who was on a statin was more affected than the brother who was not on the statin. Statins are to control hypercholesterolemia. And so I did a survey, and it seemed that in the choroideremia population, those who were taking a statin had poorer vision, but the correlation wasn't strong enough. So we undertook to do a clinical experiment, an experiment in mice. And my dear colleague has not yet put it all together in a manuscript. So some of these mice were given a high-fat diet and received statins. And what do you know? The statin was protective. So what I thought was causing a difference in between the 2 brothers as due to a drug that was coincidentally being used, not correct. So my bias was that the statin was probably not a good drug to use in a patient with choroideremia. I no longer hold that to be the truth. The electroretinogram of the mice was a lot better when they were on statins. So I'm not putting myself on statins yet, but trying to avoid the doctors. So some of this relates to the amount of protein that's present. There must be a very discrete, small amount of protein that enables enough visual function to be normal. If you're missing the whole gene, you're not making any protein. So those individuals, unfortunately, have no protein being made. And so there is that difference.
Here.
Oh, sorry.
I know I asked you this question many, many years ago, and I don't know if the answer is any different, but I had asked you in the past about supplements of DHA or lutein, if it has any protective effect on the retina.
Definitely. We're all very, we're in the Midwest. I think it's the Midwest. And I was in Alberta. I once quipped at somebody to say that fishing is not very good in Alberta because I thought the lakes froze to the bottom. But so people are not eating much fish. They're relatively DHA deficient. Many individuals are DHA deficient. DHA is docosahexaenoic acid. This is a very long chain polyunsaturated fatty acid. It makes up 50% of your retina. And this is the part of the membrane of the outer segments of the photoreceptors that are being nibbled off by the retinal pigment epithelium and then regenerated. But obviously the body needs to have more DHA if it's deficient, even though it's being recycled. And so there's lots of information in the nutrition research to suggest that DHA is protective, important for vision health. And so yes, the long and short of it, there's enough evidence to say that DHA will be of benefit, not at risk for other medications. It has GRAS status. GRAS, woo. That's one S. It's an acronym, generally regarded as safe. You could take a lot of it. I take one capsule every morning. If you're old enough, you used to get your vitamin D in these cod liver oil capsules, but these capsules are quite large. And am I answering the question, or am I too far off the mark? So,
So, Dr. Mack, if you could finish up with this answer, and then, of course, we thank you again for your presentation, and there will be opportunities for many questions down the road, including in the Doctors In session on Friday afternoon. So, when you finish up, Tara Driscoll is going to take this stage and introduce our next speaker.
okay, well, good luck. And thank you very much for the invitation.